Time travel is not science fiction, it's scientific fact. Yes, you read that headline correctly, and it is proven, as some individuals have already demonstrated time travel in small increments. Is time travel possible? Short answer, yes, and you're doing it right now, hurtling into the future at the impressive rate of 1 second per second. You're pretty much always moving through time at the same speed, whether you're watching car moving or tree growing. But this isn't the kind of time travel that's captivated countless science fiction writers, or spurred a genre so extensive that Wikipedia lists over 400 titles in the category movies about time travel. In franchises like Doctor Who, Star Trek, and Back to the Future, characters climb into some wild vehicle to blast into the past or spin into the future. Once the characters have traveled through time, they grapple with what happens if you change the past or present based on information from the future, which is where time travel stories intersect with the idea of parallel universes or alternate timelines. But before we get into that, we need to talk about time first. When we think about time as a construct, the units of measurement humans have created, such as the second, minute, hour, day, week, month, year, decade, century, etc., and this has been useful to human beings for various reasons. But what exactly are we measuring? Are we measuring something that truly exists? Or have we simply invented something out of necessity? One way to think about that question is to think about a human being's life. It is finite, they are born, they begin to age, and eventually, if all goes well, they will die at an elderly age, so it would appear that it doesn't matter if we measured their lifetime in days, months, or years. Anyway, we decide to measure it in a subjective sense. From an objective standpoint, that passage of time certainly occurs. But this only describes time as it is relative to things that age, such as humans, animals, and/or animate objects' life. But what about inanimate objects? Of course, even inanimate objects are subject to entropy. As time passes, they begin to deteriorate, but moreover, we want to know if time is actually a fundamental property of the universe. Albert Einstein's equation of special relativity defines it as just that, in what we call spacetime, which marries the concept of three-dimensional space with time to formulate a four-dimensional reality. From the theory of special relativity emerges a caveat, called time dilation, which dictates how time functions or acts differently under different circumstances. In other words, while time in fact exists everywhere in the known universe, it does not pass at the same rate everywhere in the known universe under all circumstances. And there are two major variant factors or forces of time dilation that we know about: velocity and gravity. Gravitational time dilation. The closer you are to a gravitating mass, the slower time moves. For example, if you had two clocks, one close to a gravitating mass, the near clock, and one clock far away, the far clock, the near clock ticks slower than the far clock. This has been proven on Earth. By placing identical atomic clocks at different altitudes, distances from Earth's gravitational pull, we have demonstrated that over time these clocks will show a variance in times, as the far clock will show a time noticeably ahead of the near clock. And so gravity has a significant impact on time, which is part of why we know that time actually does exist beyond being a human construct, as it interacts with the force of gravity. Now, if we extrapolate this finding, increasing the intensity of the variable of gravity by applying it to something like a black hole, the densest objects known in the observable universe, as we know the passage of time will slow significantly more as we approach something with such a far stronger gravitational pull than Earth. But how far does this slowing go? Theoretically, based on the findings of special relativity, if the black hole is massive enough, and if an atomic clock could somehow survive the forces that be as it enters a black hole, it could venture beyond the very reach of time, an area of space where the gravity is so powerful that time moves at such an incredibly slow rate that it has virtually stopped the clock altogether. But that is the limit, or maximum, of gravity's ability to impact the passage of time, as the theory of special relativity dictates that time cannot move backward, it continuously flows forward, no matter what, even at a rate so slow that it is nearly indistinguishable from stopped, and this is known as the ever-persistent arrow of time. Sorry to deflate your hopes, but because of the stubborn arrow of time, something like a black hole may nearly pause time, but it cannot act as a modern-day fountain of youth and restore you to glory days. However, this always forwardly moving arrow of time, coupled with relativity, does open the window for the very real and factual possibility of traveling to the future. Velocity time dilation. While surviving a close encounter with a black hole and witnessing the future of the rest of the universe whiz before your non-aging eyes aren't even close to a practical means to travel through time, this brings us to the other existent force that can warp the property of time, velocity, in a more plausible manner with regard to time travel. Objects traveling at high speeds also experience a slowing of the passage of time. This again can be demonstrated near Earth, with atomic clocks, and the International Space Station, which orbits our planet at the incredibly high speed of 17,000 miles per hour. Identical clocks move at a slightly slower rate on the ISS than they do down on Earth because of relative velocity time dilation. Astronaut Scott Kelly, who spent a whole year on the International Space Station whipping around the globe at these ridiculous speeds, actually aged at a rate slightly slower than his twin brother, Mark Kelly, who had spent that same amount of time here on Earth where time moves a little faster, and so when Scott returned he was close to 2 minutes younger than his brother. Because of this. And this is where relativity in relation to the arrow of time comes into play. In essence, Scott Kelly is living 2 minutes in the future compared to the rest of us on Earth who did not experience this slowing in the all-encompassing arrow of time. Scott Kelly is in fact a time traveler in the smallest of increments. But if we were to extrapolate the situation with the Kelly twins, again, increasing the intensity of the variable of velocity to a maximum or limit, as we did with gravity earlier, applying say the speed of light, where the effects of time dilation would be so great that the passage of time would move so slow it would be virtually indistinguishable from stopped, similar to the effects of gravity in such proximity to a black hole, and you spent 100 years whipping around the solar system in this manner, theoretically, when you finally decided to return to Earth, everyone else you know, all of human civilization, would have aged and progressed 100 years, while you are essentially the same age as you were when you left. Only, as a side note, because of relativity, and ignoring the attrition space travel has on the human body, you would likely need to have things to keep you occupied, preventing you from losing your mind. Because, as strange as this seems, those 100 years wouldn't seem to go any slower for you from your perspective. You wouldn't age, but the time would still have to pass. In fact, you wouldn't even notice the effects relative to the rest of us, until you finally slowed your speed and came back home, to a point of reference like Earth, as a time traveler from the past. As physicist Stephen Hawking pointed out in his book Black Holes and Baby Universes, the best evidence we have that time travel is not possible and never will be, is that we have not been invaded by hordes of tourists from the future.